Hello and welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This series of 4 focuses on motion with a variable force. An important preamble is to note that because the force is variable, almost inevitably that means that the acceleration is not constant, and therefore it's not possible to use suvat. Suvat, you'll remember, depends on having constant acceleration. We're looking again at particles moving in a straight line, a simple case. We want to consider cases where the particle is subject to a resultant force that's not constant, variable in other words. So we need to begin by establishing how F varies. That will depend from problem to problem, but the three possibilities we'll consider are that the force depends on the time, that the force depends on the displacement, and that the force depends on the velocity. In principle, it could depend on combinations of two of them, or even of all three. In each case, we'll need to draw a force diagram. It helps too to draw a diagram which summarises the information that you're given. But there's our rudimentary force diagram, which corresponds to the way the question's set up. The question we begin with is what's F? So here is how we would generally proceed. Once we've got the forces acting, we can write an equation based on Newton's second law, and that will depend on having drawn a good force diagram to make certain we include all the forces which are acting to get them in the right direction, and that we use the correct combination of signs in the result. Once we've done that, we can proceed to analyse the equation. And in this first instance, we'll start with one where the force is defined in terms of time. So here we have our first problem, a mass of 2 kilograms. It's on a smooth horizontal surface, so there's no friction. It has an initial velocity of 1 meter per second from O in some direction towards a point A. After time t seconds, it's got a displacement x meters and a velocity of v meters per second. And the stress here is on making certain we keep sense of which is the positive direction. It's in the direction OA. So here's my first diagram, which attempts to summarize the information in the question. The initial velocity, the velocity at a general point, that's denoted by v, and the displacement x from O. And I could have included that the mass is 2. Now, to a force diagram, pretty simple in this case, because there's only one force acting. We'll have the mass showing the force and its direction and the acceleration. So from that we can proceed to F equals ma, which in this case will tell us that the force is 6t minus 6, and that's 2 times a, because the mass is 2. So that boils down to A is equal to 3t minus 3. So that's our differential equation, which we now have to analyse with whatever techniques we've got at our disposal. So there's our starting point. Now the first thing to realise is that because the acceleration is not constant, it's not really appropriate to denote it by A. We need to think that the acceleration is in fact the gradient on a velocity time graph. So rather than implies A equals, we need implies dv by dt equals. So we can integrate that in the ordinary straightforward way. V will equal 3t squared over 2 minus 3t over 3t, that's correct, and then plus a constant c. 3t squared over 2 minus 3t plus c. That's not a very clear plus sign. There we are. So our next step is to work out what the constant of integration is. That will come from the initial conditions. When we've got t equals 0, we've got x is equal to 0. So looking at that, we've got v rather is equal to x is certainly 0, but v is equal to 1. That's the relevant issue in this case. So if we use that in the equation, it becomes apparent that c is equal to 1. So finally we can say that v is equal to 3t squared over 2 minus 3t plus 1. So that's our first step. Okay, then, having got that far, again we need to realise that v is not terribly helpful. We need to think of that as ds by dt, because the velocity is the gradient on a displacement time graph. So integrating once more, that tells us that s is equal to t cubed over 2 minus 3t squared over 2 plus t plus another constant. Okay then, so we can now look at that result and use the initial conditions once more. This time we do use the x is equal to 0. So when t is equal to 0, x equals 0. So pretty trivially we get that k also is equal to 0. So our final result is that x is t cubed over 2 minus 3t squared over 2 plus t and nothing else. So by this stage then we've got an expression for the acceleration that was given or deduced very quickly from what was in the question. We've got the velocity and we've got the displacement. So there's our final result for x, and we can move on to illustrate that information on the graph. Now this is the t-axis, and the upward axis is either the a, the v or the x, according to which graph you're looking at. The green graph represents the acceleration, so it's a straight line which goes through the upper axis, up and down axis at -3 and has gradient 3. And the v-axis, the v graph is a parabola, so you'll see the reddy brown parabola there. And finally the displacement is the lilac graph, which is a cubic. Now you can see various correspondences there which come from elementary calculus. I'll point out just one. If you look where t equals 1 on the v graph, which is the reddy brown one, you have a minimum where the gradient is 0, and that corresponds to a 0 on the green graph. That corresponds to the fact that the acceleration is the gradient on the A graph is the gradient on the V graph. And there are other correspondences of that kind. Well, that brings us to the end of this particular presentation. The next one is on force as a function of displacement. You might like to anticipate what difference that will make to the argument.